Hey everybody, welcome back to Young Engineers of Today. I hope you all had a good couple of days. I hope you're ready to continue with the Raspberry Pi, because that's exactly what we're going to do. As I understand it, you guys finished off with the environment sensor on it, so the temperature, pressure, and humidity, which I think is pretty neat. Um, Obviously, your mileage may vary, but I think it's pretty neat that the Sensat includes that sort of thing. And we're actually going to continue with um, we'll start out with that, and then we'll move on to orientation. Just in case you want the emulator, I will link it in the chat box so that you guys have it. How's everybody doing, by the way? Y'all doing well? Oh, no, that's totally fine. That's completely reasonable. You don't need to apologize for that. I'm glad you have power now. The YouTube videos, I believe, went up today. So I'll spend a little bit of time reviewing. I'll write the code for the basically there was some code that you guys worked on Monday, and there's going to be a small addition that we're going to make to that code, and I'm actually just going to rewrite it from scratch, so that we can do a little bit of review over what that was. The temperature seems inaccurate due to the heat produced by the Raspberry Pi itself. It's possible, although the Pis don't tend to run terribly hot. Though I guess yeah, they can get a little warm. What's your temperature sensor reading? 95 degrees Fahrenheit. Okay, that is a little warm. Definitely. I know there was a person in the other class whose temperature sensor was reading like 90 degrees Celsius. So some of them can be maybe a little bit busted, but by and large, it's not the end of the world. But if we if it really becomes an issue, I'm trying to look into a way to maybe resetting the temperature sensor or getting an adjusted reading or something like that, so we can at least get something that we can work with, so that you guys can at least have a functioning temperature sensor. But in the grand scheme of things, it shouldn't affect the barometer or the well, actually the I believe barometers for both humidity and pressure, if I remember correctly. Anyway, it shouldn't affect the other two measurements, and it shouldn't affect the IMU on the Raspberry Pi either. So at the very least, you'll be able to do other stuff with the SenseHat. So the idea on Monday was that you got to be able to, well, you got your SenseHat reading the temperature, pressure, and humidity, and then writing it out on the LED display on it. Now, the SenseHat has been used, is currently, and will continue to be periodically used by astronauts on the International Space Station, for experimentation and stuff like that. They actually sent a SenseHat up there with a Raspberry Pi, and then they got to mess around with it and do all sorts of stuff. But there are very strict conditions that the atmosphere on the International Space Station is kept to, for obvious reasons, because the outside of the ISS is space, which is, as we all know, very, very hostile to human life. Um, in fact, most life. So, according to some online documentation, the International Space Station maintains these conditions at the following level, that is to say, atmospheric conditions. Temperature between 18.3 and 26.7 degrees Celsius. So, about 60 to 80-ish degrees Celsius, or excuse me, Fahrenheit. Wow, not 60 to 80 degrees Celsius. That is incredibly unfriendly to human life. Um, Pressure, 979 to 1,027 millibars, which is roughly sea level. and humidity around 60%. So it's not dry, but it's also not humid. So it's fairly comfortable. It's actually, from just reading these values, I believe it's actually more comfortable on the ISS than it is inside of an airplane cabin, which is pretty well an accomplishment, you know, in and of itself. The fact that the ISS um, can maintain more comfortable temperatures in a more hostile environment. Now, the flip side of that is the ISS doesn't have to propel itself. The fact is, it's just sort of, even though it's moving faster than airplanes, it's really only doing that because it's continually falling and missing the Earth. Um, that is essentially what an orbit is. It's just falling and missing. Whereas an airplane has to um, has to propel itself through an atmosphere with drag and all that good stuff. The ISS doesn't have to deal with drag, so it can be built heavier. It can be built, without really fuel considerations to take into account. You just fly it up in pieces and then let it orbit, and you don't have to worry about continually keeping the space station refueled. Make small corrections with vehicles that are docked to it in order to keep it in a stable orbit. With an airplane, you don't have those luxuries, and you also have to make sure that an airplane flies um, multiple times, sometimes in a day, um, but certainly multiple times before it comes back for maintenance and things like that. So a lot of it's also set to uh, be cheaper to fly, to be more lightweight to fly, and also to have fewer moving parts that need to be taken care of. So for that reason, you pipe in the outside air and you heat it up, and um, that's basically why being on an airplane, and it also goes through a lot of filters and stuff like that. So that's why being on an airplane, you can have very dry and still cold air at a lower pressure um, than you would be, on the ground. So those are the conditions that the space station's International Space Station's atmosphere is set to. What we can do is we can set an if statement in our code to check these conditions and set a background color for the scroll. So when the scroll is reporting the conditions to us, we can update it with a background color in order to give us an idea of things are okay or things are very not okay. And it's just a simple if statement. So we say if temperature is greater than 18.3 and temperature is less than 26.7, we set the background to be green. Otherwise, we set the background to be red. And again, this is just a simple RGB value. We set red and blue to be 0, and we set green to be 100. Now, who here remembers what the maximum value is for RGB? Yeah, it's 255. So this is an important point in and of itself. We're not making this eye-searingly green or red. We're making this pretty green or pretty red, so that we can still read the foreground letters on top of that. So sometimes that needs to be taken into consideration as well when you're making some code or whatever. You fiddle with the values so that they're more pleasing to regard. So let me go ahead and delete all of this code. So now we've got our beginning code, we've got our boilerplate code, we've got our from SenseHat import SenseHat, which is just importing our SenseHat library so that we've got something to work with. And then we've got sense is equal to SenseHat. What this is doing is it's instancing a SenseHat class and storing it in a sense variable. Now that probably means nothing to you right now, but that's okay. We'll probably get more into classes and stuff like that as we get further into programming. But basically, you can think of a class as almost sort of like a self-contained little bit of a program. It can contain variables and functions. So it can have properties and behaviors. And a lot of times, classes are used to model real-life objects. In fact, they are known as objects. In fact, the whole practice of using things like classes and structs and similar sort of constructs is called object-oriented programming in order to model everything. And you will talk to a lot of people about programming as you get further into programming, if you get further into programming, and you will run into a lot of opinions about object-oriented programming, whether they are in the affirmative or the negative. It's a whole big thing, but basically, you can think of it right now. You could make a car into a class. You can make a class which models a car, and it could have behaviors like driving and honking a horn and turning on and off. And then it could have properties like color and engine type and number of doors and things like that. And then you could wrap it all up together into a class so that you could create a whole bunch of different cars that all have different properties and stuff like that, but still do the same thing. That's like a really quick, like, you know, mile overhead view. Again, it might not make really any sense right now, and that's okay. You might be sitting there going, why would I need that? As you get further into programming, you'll get a better idea of why you might want it. But for now, just understand that what we're doing is we're taking all of the things that the sense hat holds and can do, and we're storing them into a variable so that we can access them at any time. So from sense hat, import sense hat, and sense equals sense hat. We've got our library, we've got our instance class. Now we've got our while true loop. This is our forever loop that is going to be running, well, forever. So as long as the sense hat has power and this program is running, this loop will be running over and over and over again. It'll run this exactly once, and then it'll run everything after this forever. So let's start sticking in the forever stuff. So we've got T, P, and H. These are going to be our three variables that represent temperature, pressure, and humidity respectively. I did these one after another just so I could show you guys, but we're actually going to fill these with values. So T is going to be equal to sense.get temperature. So as you might imagine, this is a function that gets the temperature currently being read by the sense hat's temperature sensor. Then we've got P, which is equal to sense.get pressure, which is the pressure sensor. That's going to feed it into P. Pretty straightforward. H is sense dot, take a wild guess as to what this is going to be. If we're getting the humidity, it's probably going to be get humidity. Boom. So sense.get temperature, sense.get pressure, and sense.get humidity. These are going to be fed into temperature, pressure, and humidity respectively, and I've given them incredibly unhelpful one-letter variable names. Generally, you don't want to do that. This is known as bad programming practice. You generally want to have like temperature, pressure, and humidity. But we're just going to do this for simplicity's sake. Why, you might ask? Is this considered bad programming practice? It's because you want to make things as easy for you to read as possible. And let's say you wrote this code and then 6 months later you came back to it, and you'd have to hunt through the code in order to find out what exactly T, P, and H are, respectively. Now, there's something to be said for having things be typed easily. So T, P, and H are a lot easier to type than temp, press, and humid, respectively. But it's always a struggle between easy to type and easy to read and keep track of. So next, what we're going to do is we're going to force these values to one decimal place. So round T1. Same with P, round P1, H, round H1. So what exactly are we doing here? Well, whenever we get the temperature or the pressure or the humidity, the sense hat's going to give it to us like in 4 decimal places. So it's going to be like, oh, the temperature is not just 18.3, but it's 18.3691. We want to continue repeating getting those variables and go on to the rest of the program. So are you saying like, so it's just going to grab these always and forever? Oh, and not go on to the rest of the program. Okay, you bring up an interesting point. So let's say we've got do stuff with variables here. So you're saying that it'll continually do this part and not move on to the rest of the program? Am I correct in that assessment? Okay, I see where you're going with that. Notice how these lines right here are all indented as well, which means that these lines are also part of this while true loop. This line right here where we do stuff with the variables is also indented. So it's also a part of this while true loop. Now, here's the thing about a loop. A loop will run, again, there's always that caveat with exceptions that exists in programming, but assume as a rule, a loop will always run through all of the lines of code inside of that loop before it repeats itself. So if we were to run through this step by step, it'll get temperature, it'll get pressure, it'll get humidity, but the loop is not done because there are still more parts that are there are still more parts to the loop. So it's going to move on to the next part of the loop. And it's going to run the rounding for each one. And then it's still not done. There's still more parts of the loop. So it's going to run any other lines of code that we have that are a part of that loop. Once it hits that last line of code, last part of loop, once it hits that last line of code in the loop, then it'll run back to the top. Then it will refresh the temperature, the pressure, and the humidity. Then it will do the rounding again, and then it will do stuff with the variables all over again. So in a sense, what we're doing is maybe a little bit ineffective, but we're also kind of working with limitations of the program here, or excuse me, the medium, which we can work around. But for now, you'll see what I mean when I get to this point. This is going to offer exactly what we need right now. So let's do the next part, which is going to be determining the background color. So we've rounded these to 1 decimal point place each, excuse me. Okay, yes, so that might be why you were running into an issue. You always want to make sure. So that's another point I want to bring up. Those of you who are just getting acquainted with Python, a very important thing to know is that white space in terms of indentation is very, very important with Python. So we've got this while true with the colon, which announces that a while loop is starting. However, Python will only consider things that are indented one level from that to be, or excuse me, will only consider things that are indented from that to be a part of that loop. So if I do something down here that's not indented, that's not a part of the loop. This is not a part of our while loop because it's not indented. As soon as it is, it's now considered a part of our loop. So you always want to make sure that if you want something to be a part of a loop or an if statement or something like that, that it's always indented one level from when you announce that, which actually brings us into our next part. We're going to determine the background colors, and so we're going to use if statements. So if temperature is greater than 18.3 and temperature is less than, 26.7, so that's our if statement. Notice how it indented it one level further after our if statement. So now, whatever we type here, in this case, bg is equal to 0, 100, and 0, it is a part of the if statement because it is indented one level up from the if statement, 1 tab, or 4 spaces. Because the if statement is indented one level up, from the while loop, the if statement is a part of the while loop. So we've got a statement here which is a part of an if statement, which is a part of a while loop. So you can nest them by doing that as well. And all you have to do is make sure that you've indented them an appropriate number of times. And that's either going to be one tab for each level or 4 spaces for each level. And you will find people who get very territorial about whether it should be 1 tab or 4 spaces. So let's go back 1 indentation, because nothing else is going to be a part of this if loop. However, we are going to have an else, or excuse me, this if statement. We are going to have an else though, so else. So if the if statement is not true up here, if the temperature is less than 18.3 or it's greater than 26.7, we're going to execute the else, which is going to make the background equal to 100, oops, 100, 0, and 0, which is going to make it red. So as you can see here, this else statement is not a part of this if statement. So it's not indented from the if statements. However, it is a part of the loop, so it's indented from the loop. So hopefully that sheds a little bit more light on it. Now, vertical white space doesn't matter. I could do this, and my program will run just as well as it will when I have these spaces. However, I put those spaces in so that I can make it a little bit easier for me to compartmentalize and read in my head, because I am slow and I have hard time reading code. But you know, as your code gets larger and stuff like that, you'll tend to want to do that as well, so that you can read your code more easily and keep track of it. There's sort of this term like mental RAM, where we have brain space that we can devote to sort of running through the meandering passageways that a program can become and keep track of all the things that are going on so that we understand. The Raspberry Pi cannot do brown. Yeah, that doesn't surprise me. But yeah, so we keep track of all the things as it's going through our head. And doing things like making the code harder to read or using unhelpful variable names and stuff like that, well, those will require us to fill up more of our mental RAM keeping track of what's going on in the program. As we make it easier for us to understand the flow, we can start grasping larger and larger chunks of the program and thus write more and more complex and larger programs on our own so that we can be, better coders. So that's going to be our if and else statement. All simple. If it's within an acceptable range, we're going to make the background green. If it's not, we're going to make the background red. Boom. Nice and easy to read right off the outsets. Now we're going to build our message. So this is going to be MSG is equal to some stuff in double quotes. So we're going to say temperature is equal to 0 in curly brackets. Pressure is equal to 1 in curly brackets. And humidity is equal to 2 in curly brackets. And then we're going to put a dot, and we're going to say format. Notice how this dot comes right after the double quote with no space. So it's just double quote, dot, and then the word format, no spaces. And then in the parentheses, we're going to put T, P, and H for temperature, pressure, and humidity, respectively. So what did we do here? Hold on, let me okay, there we go. So we can take a look at the whole line. So we've got temperature is equal to 0, pressure is equal to 1, and humidity is equal to 2, which are hard-coded values. However, we're also saying that we want to put the, good Lord, there we go. We're also saying that we want to put the temperature, pressure, and humidity into a hard-coded string? How does that work? Well, this is a holdover from C, sort of. C does a very similar thing. C and C++ and C# and Java and blah, 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 blah. They all do a very similar thing in the respect that there are these sort of specialized characters. That is to say, in this case, it's these little curly brackets with a number inside of it. Anytime you see little curly brackets with a number inside of it, you're telling it, hey, all right, so I'm going to give you some variables right after this string, and I basically just want to have you take the contents of those variables and replace the curly bracket number curly bracket with whatever the contents of those variables are. So in this case, curly bracket 0 curly bracket is going to be replaced with the contents of temperature. Curly bracket 1 curly bracket is going to be replaced with the contents of pressure. Curly bracket 2 curly bracket is going to be replaced with the contents of humidity. And the only reason it knows which to do is because we've numbered them. If we did all zeros here, they would all be filled with the first value, in this case, temperature. So we do 0, 1, and 2 so that we can do the 0th, 1st, and second value respectively. So let's go down to the next level, or the next one. Boom. Okay, so there, now that's readable at least. And then finally, the coup de grace on all of this is we're going to sense.show message, and we're going to feed some values into this message. So the message function. So it's going to be message scroll speed is equal to 0.05, and back color is going to be equal to BG. There we go. So show message can take a few different parameters to it. First off, it can take the message that it's going to display. Then it can take the scroll speed, which is the speed at which it scrolls, unsurprisingly. Then it can take a back color, which is the background color. So what we've done is we've fed all three of those variables to it. So it should give us our temperature, pressure, and humidity at a nice lazy scrolling speed with a nice helpful background color. So let's go ahead and let's test it out. I'm going to hit stop. Oh, that's why it was running so slowly. It was still printing a whole bunch of stuff out to the console with the accelerometer. Whoops. All right, so we'll hit play again. Bring that down, and as you can see, you can see it if I don't cover over with the. Oh my goodness. Down there. Go away. Okay, we know you're powered by Trinket. Stop. There we go. All right, so I'm gonna expand the Raspberry Pi a little bit so that you can see it. Equals 43.8. So it's going to be that was the humidity. So the temperature is equal to 21.1, then comma, then pressure is equal to 1013, then humidity is equal to 43.8. It takes a really long time to scroll through all of it, and it's actually kind of hard to read on the emulator here. But the nice thing about the emulator is we can also say that, oh, it's 120 degrees Celsius. There is currently water boiling out of the oceans. Now, once it runs through its cycle here, you'll see it update to be red. And this might help give you an idea of how a loop executes. See, now it's red, and it actually becomes a little bit easier to read the printout on it because it's not as bright a color, ironically. But the temperature is super high. It has no idea how to read that temperature, and it's really unhappy about that. And so it's super red to reflect that. So this maybe gives you a little bit better of an idea. Notice how it doesn't actually update until it's run through its entire loop, until it gives us the entire temperature, pressure, and humidity readout. Then it might update to be green again once the temperature is fine. So let's actually go down to 20 degrees. So it'll turn green as soon as we get done with the humidity. So thinking about that in our heads, that's happening because it has to execute all of these messages before it reads the variable again. So as we can see, it turned green, which meant that it read through the entire message, and then it went back up to the top of our loop and started reading the temperature, pressure, and humidity again. Realized that everything was okay after it went through the if statement, and then updated the background color appropriately, and then printed out the message as it should be with the nice green background. So with that right there, we've just expanded our program to show a nice color in the backgrounds based on external ambient temperatures. Now, if you're not running the emulator, I'm not expecting you guys to go run over to the thermostat and set it to be 40 degrees Celsius. What you can do, if you want to test things out, is you can change these values here. So let's say that if the temperature was below 21 degrees Celsius, we should actually see it update with the red. Oh, I believe we actually, for me, I have to update it, which puts the code back into the SenseAt. So we should see, yep, look, our temperature is red now. or excuse me, our background is red now. So we'll go back to 18.3, stop and run, and we're back to green. So you can do that at home too. If you know what the temperature is in the vicinity of your sense hat, you can expand or contract the if statement in order to bring your temperature within or outside of the acceptable range in order to test that background color. Because again, I'm not expecting you guys in the interests of testing to make the temperature in your place super uncomfortable or downright dangerous. So that is the atmosphere sensor on the Sense Hat and the Raspberry Pi. Any questions? Okay, good enough for me. So let's stop this and we'll get into the IMU, or Inertial Measurement Unit. So the Inertial Measurement Unit is a pretty cool suite of stuff and things. The IMU contains a gyroscope for detecting which way up the board is, or detecting which way is up for the board, an accelerometer for detecting movement, and a magnetometer for detecting magnetic fields. So a magnetometer, why do you think that one's included? What magnetic field are we detecting exactly? Yep, exactly. It's the Earth's magnetic field. So that means that our sense hat can tell us where north is, at least magnetic north. There would be a little bit of fiddling about to do, but I'm sure you could write a function that would also tell you where geographic north is. So you could turn your sense hat into a compass. You could turn your sense hat into a rudimentary GPS. It's not going to be able to pull satellite data and stuff like that, but based on these three things, it could get a decent idea of where you stand on the planet, simply based on gathering its initial, like you feed in a set of GPS coordinates to it, and then it works from there. It detects which way is north, and then it senses your movement as a person, so it gets your velocity, which is a direction and a speed, and it uses that to determine how far you've moved from your initial position. So you could actually have a very simplistic GPS on your Raspberry Pi. Now that also requires it having power and stuff like that, which is a whole other beast and everything. But you could rig up a battery hooked up to that provides the proper amperage and voltage you know with a micro USB so that it could be plugged into it and blah blah blah. You could solve that problem too. But you could, yes, you could turn your Raspberry Pi into a GPS. So the gyroscope detects pitch, the accelerometer detects roll, and the magnetometer detects yaw. Those are simply the three axes of motion. And you've seen all of these in a plane before. A plane does all of these things. That's pitch. So pitch is simply the plane tilting up and down, so as you can see, like a gyroscope. So it's like taking off or landing. Roll is the plane spinning, like if you ever played Star Fox 64 do a barrel roll, which technically that's not a barrel roll, that's an aileron roll, but that is a roll. And then you've got yaw, which is a left and right movement that does not involve spinning. And that's like steering a car. A plane can do that too. Um, And those are the three axes that a plane can use for motion. So once again, pitch, I know, right? Me neither. Roll and yaw. And the Raspberry Pi, well, more specifically the SenseHat, can detect all three of these things. Pitch, roll, and yaw. And we can find the orientation of the SenseHat using the sense.getOrientation method. So let's go ahead and let's write a program that can do that for us. So now we're going to do something a little bit different. Normally we've done the show message, which is printed out onto the SenseHat. We're going to use a print function, which will print it out directly to a console. So it should print it out to a console on the Raspberry Pi, whether you run it through the command line or through some sort of little IDE that provides a console as well for Python. I believe idle will also print out values in real time, if I remember correctly, if you run it through there. But we're going to keep our basic skeleton. So we've got our from SenseHat import SenseHat and sense equals SenseHat, and then while true with our indentation. And we're going to grab our values. So orientation, which as you can think is orientation, is equal to sense.get orientation. Boom. Sense.get orientation. As you might imagine, get orientation is going to get you the SenseHat's orientation, and we're going to feed it into orientation. Pretty straightforward. Then we're going to have pitch, roll, and yaw. Another thing that's very important as a programmer is to have consistent naming conventions. So we named it pitch, roll, and yaw. The full words here, I can't exactly do T, P, and H later on in the program because those are inconsistent naming conventions. These are things that you'll get a feel for, as if and when you do continue in programming. But anyway, so pitch. How do we get pitch? Well, it has to do with the way that orientation feeds us information. So when we get orientation, just imagine I wrote out the entire word orientation and fed it into the orientation variable. What it is feeding into it is it's basically feeding into it three variables. So you're going to have one value, you're going to have a second value, and you're going to have a third value. It's going to feed three values into orientation, and orientation is going to keep track of those values. And then we can reference those values by name because they'll also come handy dandy with a label. So we're going to have pitch, roll, and yaw. So that these values are then going to be labeled with the pitch, roll, and yaw. And anytime we want to reference one of these, let's say we want the pitch value, we're going to reference it by name. And it will go, okay, I know what you mean. Here, I'll feed you the value back. So we're actually going to do that here. So pitch is going to be orientation, and then we've got our square brackets, and then we got single quotes. So orientation pitch. This particular construct is known as a dictionary because you can look up an answer by its, like, if you go to a dictionary and you want to look up the meaning of a word, you search for it by word, and then you have a whole bunch of information, which is generally the definition of the word that's related to it. So, you can go to pitch in the dictionary and get all that information about pitch. So that's what we're going to do here is we're going to go to orientations dictionary and we're going to get all that information about pitch, which is going to be the value of pitch. Now you might be saying, well, so at any point I can just go and get pitch and, why pitch specifically? Is it smart enough to know? Well, not really. It's because the person who wrote this library was smart enough to label it pitch so that you could get it easily. In fact, the person who wrote the SenseHat library is a very, very programmer-friendly person because a lot of this stuff is very cleanly labeled and very easy to use. So orientation pitch allows us to get the pitch value. Surprising no one, orientation roll allows us to get the roll value, and orientation yaw allows us to get the yaw value. Pretty straightforward. Then when that's done, we're going to print that information out to the console. So this is going to be a little bit different. So instead of sense.showMessage, this is just going to be print. And then in print, we're going to have parentheses and then double quotes. And we're going to say pitch equals, again, curly bracket 0 though. Roll equals curly bracket 1 and yaw equals curly bracket 2. And then closing double quote period format with no spaces, pitch, roll, and yaw. Just like we did with the show message, except instead of temperature, pressure, and humidity, we're doing pitch, roll, and yaw. But it's the same idea. So now, if we're to run this, we can't really read anything because it's being printed out in the console down here. But as you can see, I've got pitch, roll, and yaw, 337, 334, and 63, with all of this information afterwards. It's just a whole bunch of decimal places. But as I rotate the pi, you can see these values update. So it's keeping track of all this stuff. So if we were to do this, I think we can fix it. Boom. So now we've got our pitch. Then we can fix the roll. It's not always 100% smooth on the emulator. And then yaw, feed it back. Whatever, you get the idea. So these give us the different values, and these are all being printed out down here. Now, there is an update to this that we can do. Instead of getting the instead of getting the value of the orientation, we can get the acceleration instead. And that's kind of interesting in its own right too, because rather than getting the current state of it, we can get the basically the direction that it's moving in. So you can click and drag the SenseAt in the emulator to see the values change. Another way to detect orientation is to use the sense.getAccelerometer_raw method, which tells you the amount of g-force acting on each axis. If any axis has plus or minus 1 g, then you know that axis is pointing downwards. In this example, the amount of gravitational acceleration for each axis is extracted and then rounded to the nearest whole number. So we can cover that in a second, but basically, yeah, it's going to give you the amount of g-forces acting on each axis. If we're just holding our Raspberry Pi in our hands and we turn it and stuff like that, we're going to get values from 0 to 1. If you start flinging it around, you're going to get values that are greater than 1 and less than -1 in specific directions, but I don't recommend doing that. But for now, we're pretty much going to get either 0, 1, or -1. So I'm going to do this one really quick. I know it's 8:48. You guys don't have to do this one along with me, so don't worry, because I'm going to go a little bit faster than normal. So we're going to go, whoop, we're going to go. Acceleration is equal to sense.getAccelerometer raw, and then x, stop it, stupid autocomplete, y, and z is going to be equal to acceleration, acceleration, and acceleration. X, Y, and Z respectively. And then these are going to be X, Y, and Z, and X, Y, and Z. So now if I get the raw accelerometer values, boop, boop, boop. Oh, I forgot a thing. Format X equals round X0, Y equals round Y0, and Z equals round Z0. Let's try that again. So now we're only going to get -1 or 1 values. And as I rotate it, hey, look at that. These change around. So as they get different amounts of g-forces acting on them, we know that it's oriented in certain ways. So right now the y-axis has 1g on it, and the z-axis has -1g. So we know that the z-axis points upwards this way, whereas the y-axis points downwards that way. And this is a three-dimensional sort of a thing, which is why it looks weird. There's no real convenient way to draw 3 axes on a 2D plane. So I apologize in advance for that not really making any sense. But imagine that red arrow was kind of coming out towards us. And that's going to do it for today. That got us through the IMU on the SenseHat. Now you're going to be able to go through and use more of that stuff and tie it into larger programs on Monday and Wednesday and stuff like that, so that you'll get more familiarized with what you can do with those values. That is going to do it for today. So what I'm going to do is I'm going to go ahead and do the poll questions, and then once we've done the poll questions, if you have any questions, I'll be here. Otherwise, you're more than welcome to head out and have a great weekend.